Okay, this is our first lesson in networks. Unlike everything else we do in standard mathematics, this isn't really building on something that we've seen in junior maths. So while you might not have seen everything we did in the last trigonometry unit, you would have seen trigonometry before, whereas this is an area of maths that is relatively new. It's also a relatively new area of mathematics generally. It dates back only to around about the 1700s, as opposed to things like Pythagoras, which dates back to many, many years BC. It is an area that's got a lot of new terms, so it might be somewhere you might want to use flashcards and those sort of things just to understand the terms. So networks don't have to be about computers, and in fact network theory has been around long before computers. But obviously it's helpful to think about it in terms of computers because we think about linking and joining computers, but we can also think about networks in terms of many other things. Obviously there's a road network, a rail network, those sorts of things. But as well as that, you've got a friend network. So if you think about particularly social media, you've got friends, and those friends have friends, and they might not be the same friends that you have, and then those friends of those friends have further friends. And so these are sorts of things that we can sort of follow and graph using network theory. So at its most basic, a network is made up of vertices and edges. Now, depending on what you're reading, you might see those two terms used differently. Vertices, sometimes you'll see referred to as nodes. So if you see nodes being written, then you just know that nodes and vertices are interchangeable, although in the HSC syllabus it's always referred to as a vertice. So the vertices are our dots, and the nodes are the edges are the lines that join our dots. The edges can have arrows, and that's when we've got a directed network. So, for instance, we might have only a one-way flow in a network, and we might have we'll use an arrow there to show that. And then, as well as that, the edges can be weighted depending on what we're trying to model. Sometimes a weight on the edge will make sense. So, for instance, a weight might be kilometers, or it might be meters, or it might be dollars to join two things, or something like that. So usually the number is all that appears on the network diagram, and then somewhere near the network diagram there'll be some sort of legend. So just looking at this little network that we've got written here, there are 4 vertices, A, B, C, and D. So if I just highlight A here, there's vertice A right there. Okay, that's that little dot there. Okay, there are 6 edges. So if I highlight edge AB, for instance, there's edge AB joining A and B. Edge CC is a loop. So if I just do that with pink highlighter, you can see that we've got a loop where there's a loop that leaves C and goes nowhere. Doesn't make a lot of sense in relation to some areas of network theory. So if we think of computer networks, there'd be no point in laying a whole bunch of cable going nowhere. But if we think of a road network, there could certainly be a road, maybe a tourist route or something like that going not to another town, but maybe joining up farms and those sorts of things. So vertex B has a degree of 2, as 2 edges are connected to the vertex. So if we look at vertex B there's 1 and 2 vertices that run off it. Okay, edges that run off it. It also has an even degree because 2 is an even number. Vertex A has 3 edges. So if I just pull up another color here, we'll go with maybe that color. So vertex A, we've got 1, 2, 3 edges, so it has an odd degree. Okay, so when we draw a network diagram, we just need to first sometimes you need to sort of draw it twice, but generally the best idea is to sort of start with drawing your vertices. So if I start there, I'm drawing a network for these towns. So there's Wyangry, and up here I'm going to call that LC for Lynch's Creek, and down here I'm going to call that CC for Collins Creek, and over here I'm going to have GP for Green Pigeon. And then down here I'm going to have an MC for Mahoney's Crossing and a HC for Horseshoe Creek. Then there's an FP down here, Fawcett's Plain. There's an NP here for New Park. I'm going to put these dots in. I might need to move these around in a minute, we'll just see. And we've got a C over here for Kawangla. Probably should have started joining these in. I'm going to have to call Kilgara KI, because obviously Kyogle is going to need to be dealt with differently, so KY, and then we'll call Geneva G. And so we just start drawing these connections. So from Wyangri I can go to Lynch's Creek. I might use a different colour for my connections, so I can go like that. And then I can go from there to Collins Creek. From Collins Creek I can go out to Green Pigeon, but I can also go down to Mahoney's Crossing. And then from Green Pigeon I can go down to Horseshoe Creek, but at the same time Mahoney's Crossing and Horseshoe Creek are joined. And from Horseshoe Creek I can go down to Fawcett's Plain. From Mahoney's Crossing I can go down to New Park. From Fawcett's Plain I can go out. No, actually no. Cool. I can go Kyogle to Kawangla. You don't quite get to Fawcett's Plain when you go to Kawangla, so that seems to be much more the case. So because I don't need to go to Fawcett's Plain, even though I need to travel in the direction of Fawcett's Plain, because I don't quite get to Fawcett's Plain, we just draw a straight line to Kyogle. Kyogle joins to New Park, and where do we have Geneva? It's just fallen off the side of here. I need a node for Geneva, so I better put that there. So Geneva joins to Kyogle, and Kilgra joins to Wyangri, and also joins to New Park. And there's my network. Now I could rearrange that network to be a little bit more square or something like that. We don't have to make the network to scale. We don't have to make the network even look like what it looks like in real life. We're really just chasing down, we're just really looking to see what are the connections and how can we manipulate those connections. We're not really interested in, oh, this is what it looks like in real life. That's not really important in this case. Okay, so example 2 for the network shown, find the number of vertices. So the vertices, I'm just counting each of these spots where the edges join. So in that case, there's 5. The number of edges, if I use the blue highlighter, I've got 1, 2, 3, 4, 5, 6, 7. So 7 edges. The degree of B, so for the degree of B, we're just going to count. So I'm going to use a purple texture here. We're going to count how many edges come off B. Now, importantly, obviously we're going to have 1 there, 2 there, and obviously 3 there. But in the case of a loop, we count both sides of the loop. So the degree of B is 4. So there's 4 edges coming off vertex B. The even vertices. So obviously B's even because it has 4 edges. A's also even because it has 2. D's even because it has 2. C's even because it has 1, 2, 3, 4. And E's even because it has 2. So we can just say here all vertices are even. State whether it's a directed network. So for it to be a directed network, there would need to be arrows. So I could say something like there are no arrows so this is not a directed network. What is the weight of edge BD? So if we look there at, I'll use my little rainbow pen for that one. If we look at edge BD, oh, I probably shouldn't use rainbow because now you can't see the 16, or maybe I'll just put it down here. If we look at that edge there, it's got a weight of 16. Okay. If the weights were distances in kilometres between villages, what would the loop BB represent? So we've got a road between roads between villages, and we've got this loop going to no villages. And there's a whole manner of ways in which we can think about it, but it's just a road that does not connect to another village. Now that could be like a tourist route, it could be a road up to a lookout or something like that, or it could just be a road that goes out to some farms around the area, but doesn't actually connect to any other towns. It just connects to farms and people who live in that area. And that's the end of today's lesson. There's a link down here for an Education Perfect activity, which will also be on Google Classroom. It might be a nice starting point just to get those definitions and all those sorts of things working correctly for you. But yeah, have a go at the questions. You won't find them too hard. The difficulty with this is just going to be remembering what all those terms mean down the track. So while you won't find it hard today, make sure you spend the time on it, because you want to sort of cement that into your brain so that when you're asked questions about this later on, you can immediately recall what those terms mean. That's the end for today.